Welcome to the second part of the lecture. Here we talk about stress tensors. You remember our mitral valve. Remember that we can find a traction vector for any point inside a body. Well, we can define a stress tensor for any cubic element of the body. On each plane of the surface, we can find the traction vector and then the associated normal and shear stresses for that surface. Let's see how we do it. This is how we find the stress tensor. Assume a rectangular Cartesian coordinate at point P and a tetrahedron slice of mashed potato named A, B, C, P with height h. The tetrahedron surface normal vectors are n perpendicular to the base surface, minus E1, minus E2, and minus E3 for each of the side surfaces that are aligned with the reference frame surfaces. So basically we have n1 equal to minus E1, n2 equal to minus E2, n3 equal to minus E3, which in vector format it's basically 0, 0, 1. For the area of these surfaces, based on the area of the base surface, ds, we can write ds of I, each of the side surfaces, is equal to ei, the normal of that surface, inner product with n, the normal of the base surface, multiplied by ds, the area of the base surface. It is simply NIDS, that's a scalar value. That's how we calculate it. For example, for ds1, the normal is minus E1, which is 1, 0, 0. So basically the area of that surface equals to ds1 is equal to inner product of E1 with the normal surface, normal vector of the base surface, multiply by ds. It simply becomes the first element of the normal vector of the base surface, multiplied by ds. Similarly, for ds3, it is n3, the third element, ds, and for ds2, it's n2, the second element, ds. For the forces acting on these surfaces, we can use Cauchy stress principle that says the force acting on a surface is equal to the traction or a stress vector of that surface multiplied by the area of that surface. Based on that, we can write the equilibrium of all forces acting on this tetrahedron, which is the force acting on the base surface with normal n plus the forces acting on the side surfaces. This is basically Fj of E1 plus Fj of E2 plus Fj of E3 plus the body forces. If we use the Cauchy stress principle, we get Tj of n ds minus Tj of ei ds of I, which we already see that it becomes ni ds plus the density Bj, the body force per unit mass, dV, the volume of the tetrahedron, which is 1/3 of hds, equal to 0. You may notice that ds is common between all the terms, so we can cancel that out. From this equation, we can find the elements of the stress tensor. Assuming that this tetrahedron is very small, so h, the height is approaching 0, we find the stress tensor sigma, which is second order tensor, basically a 3 by 3 matrix at point P. This is how the equation above simplifies to. It says the jth element of the traction vector on the surface with normal n is equal to the summation of the jth element of traction vector on the side surfaces multiplied by the corresponding element of the normal vector to the base surface. So for example, T1 of n is equal to T1 of E1 N1 plus T1 of E2 N2 plus T1 of E3 N3. We name Tj of Ei as the ijth elements of tensor, which we call the stress tensor. So sigma ij is equal to Tj of Ei. Or simply, it's a 3 by 3 matrix in which each row is the traction on one of the side surfaces. We use the stress tensor to find the stress vector on any plane passing P with normal n. So we get the Cauchy's stress formula that says the traction vector on a surface passing P with normal n is equal to n dot sigma. And note that we changed the indices for convenience, change the I and j. So Ti of n is equal to sigma ji nj. That's an important formula to memorize. In other words, we can say that the ij elements of sigma, the first subscript I is the surface normal direction of traction vector, and the second subscript j is the stress component direction. Let's talk a bit more about the stress tensor components. Now consider a cubic element of the potato. So at point P inside a body, we assume a very small cubic element with surfaces perpendicular to the reference frame directions. The 9 stress tensor components at a point P determines the traction stress vector for any plane through P with any normal n. That's basically the Cauchy's stress formula that we talked about. So the stress tensor equal to 3 by 3 second order matrix or second order tensor has 9 elements: sigma 1 1, sigma 1 2, sigma 1 3, and the rest of the elements, and it defines the stress vector on any surface with an arbitrary normal vector n passing through that point. Here we call sigma 1 1, sigma 2 2, sigma 3 3 the normal stresses, or in short, sigma I are the normal stresses. We call sigma 1 2, 1 3, 2 1 2, 3, 3, 1, the shear stresses. So basically sigma ij for I not equal to j. You see that here, sigma 1, 1, 2, 2, and 3 are normal to the planes, and sigma 1, 2, 1, 3, 3, 1, 3, 2, 2, 3, 2, 1 are parallel to those surfaces or tangent to those surfaces. Stress components on a surface are components of the traction stress vector of that surface. So each of these surfaces has a traction vector, as you see, T of E1, T of E2, and T of E3, and the normal and shear stresses on that surface are basically the components of the stress tensor associated with that surface. Other properties, the stress tensor is symmetric, so sigma ij is equal to sigma ji. Basically, for example, sigma 2, 3 is equal to sigma 3, 2. So it has only 6 independent elements. And also, we can define something called mean normal stress, which is equal to 1/3 of the summation of the normal stresses. 1/3 of sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. In short, in index notation, we can write it as 1/3 of sigma ii. You may know that that's 1/3 of the trace of the matrix sigma. Here is an example question. It says, when we analyze the stress in Mr. Potato through point P111 and a plane perpendicular to N001, we obtained a traction vector T120. Similarly, for a plane perpendicular to N2 equal to -100, the traction is T200 minus 1, and for the plane with N3 equal to 0, 1, 0, the traction T3 is 2, 2, 2. So you may notice that N1 is actually E3. N2 is minus E1, and N3 is E2. So basically, T1, the traction associated with the plane normal to N1, is TE3. T2 is minus TE2. And T3 is E1, and T3 is TE2. So basically for TE3 and TE2 it's obvious, but for TE1 it is minus T2, so equal to 0, 0, and 1. For TE3 it is 1, 2, 0, and for TE2 it is 2, 2, 2. Then the first part of the question says write the components of the Cauchy stress tensor sigma ij at point P in this coordinate frame. We've already seen that it is a matrix in which each row is the traction associated with that reference frame direction. So it simply becomes 0, 0, 1, 2, 2, 2, and 1, 2, 0. That's the solution to this first part of the question. Then it asks write the traction vector or a stress vector, a T of n for a plane perpendicular to n equal to 1, 3, 2 divided by 14. We use the Cauchy stress formula, which says that traction of the plane perpendicular to n is equal to the normal of the plane dot the stress tensor. So it is basically 1, 3, 2 divided by 14 multiplied by 0, 0, 1, 2, 2, 2, 1, 2, 0. I've already calculated that, and it becomes 0.57, 0.71, and 0.5, or basically 0.57 E1 plus 0.71 E2 plus 0.5 E3. That's the solution for the second part. Let's review some concepts. First, we talked about the traction or a stress vector on a plane with normal n at an arbitrary point. We showed that we can write Tj of n is equal to Tj of ei multiplied by ni. So basically the jth element of that traction vector is equal to the summation between the jth element of the traction vectors on planes perpendicular to the reference frame directors multiplied by the corresponding element of the surface of interest normal vector. Let me expand it and you see better. So for example, for the first element of the traction vector, we can write the first element of traction vector on plane with normal 1 and 1 plus, again the first element is 1 of the traction vector for the plane normal to E2, N2, and then T1 of E3, N3. Then we talked about a stress tensor sigma and the Cauchy stress formula. We simply named Tj of Ei as sigma ij. So basically, for example, sigma 1, 2 is equal to the second element of the traction vector on the surface normal to E1. And the Cauchy stress formula that says the traction vector on any surface is equal to the normal vector of that surface dot the stress tensor at that point. Then we talked about the normal and shear stress components of the stress tensor. These are the normal components perpendicular to the surfaces of a cube at that point, and these are the shear components parallel to the surface of the same cube. Then we introduced mean normal stress, which is 1/3 of the trace of the stress tensor, or basically 1/3 of sigma I. We can transform or rotate a stress tensor. So, for example, if the reference frame that we define the stress tensor inside it rotates, the stress tensor rotates according to this rule. If we name the rotated frame as the prime frame, sigma prime, the rotated or the transformed stress tensor is equal to alpha, the rotation matrix, which is a 3×3 matrix, sigma alpha transpose. Here it is in the index notation format. And finally, the stress tensor is symmetric in case there is no concentrated momentum acting on the system, meaning that the shear components has this relation: sigma ij is equal to sigma ji for I is not equal to j. As a result, the stress tensor only has 6 independent elements, and the other 3 elements can be found based on the other elements. Let's solve an example for transforming or rotating the stress tensor. It says, giving the stress tensor at point P in xi frame as this, find the stress tensor sigma prime at the same point, but in x prime frame, which is obtained by 45 degrees rotation of x frame about x3 axis. Okay, let's form the rotation matrix as alpha ij is equal to, so it's rotation around x3 axis, so it's going to be cosine of 45 degrees sine of 45 degrees 0 minus sine of 45 degrees cosine of 45 degrees 0 0 0 1. The rotated stress tensor sigma prime ij is equal to, we already know that it's equal to alpha sigma alpha transpose. Basically, so that's cosine of 45, that's sine of 45, minus sine of 45, cosine of 45, 0 0 1. This is the given stress tensor at point P in X frame, and here is the transformation of the rotation matrix. And our already have calculated the final solution, which becomes 4, 0, 2 square, square of 2, square root of 2, 0 minus 2 minus square root of 2, square root of 2 minus square root of 2 minus 2. And finally, here is a question for you to solve during the break time before we start with the third part of this lecture. It basically gives you the stress tensor and asks to find the attraction or stress vector on a plane with given normal vector.